Radiology went digital decades ago. Now, pathology is catching up and it's bringing AI along for the ride. In this video, which was a presentation I gave for a group at Cincinnati Children's, we're diving into how AI is transforming pathology, comparing it with radiology's journey, and exploring the game-changing technology that's making it all possible. From foundation models to digital-first practices, I'll show you exactly where pathology is heading this year. Let's talk about pathology's digital leap. So I'm a veterinary pathologist, as you've heard, and you might have seen some of my YouTube videos on the channel or listened to the podcast, or maybe we are connected on LinkedIn because that's where I hang out virtually and digitally to spread the word about digital pathology. But I'm also someone who started digital pathology practice in one way or another in 2016. And I studied for my boards with digital pathology slides. And I recently learned that now boards are digital, so it's not a big deal anymore. So I might want to change this achievement to something else. But at the time I was passing my boards, it was actually the first time that veterinary pathologists moved to the same center in Florida, in Tampa, where the MD pathologists were passing their boards. And even though we were still doing this on the microscopes, I was studying on digital slides because I had trouble with my microscope. I work at Charles River Laboratories, which is a CRO, and I also use digital pathology so that I can go with my kids to Poland and still keep working, because we go for weeks at a time, couple of times a year. And this is personally very important for me to be able to do both, work and go to Poland. So today, I'm going to give you an overview, and based on a few conversations with radiologists, we're going to compare pathology and radiology, and there are going to be a few real-life examples. And we're going to talk about image analysis for esophagitis, colorectal cancer, and I'm going to give you an example of a very advanced digital practice based on publications and on conversations I had in the podcast. And we're going to talk about repositories and decentralized ways of training models, and the new buzz of foundation models. What is agentic AI? And I'm going to show you the earring test. I don't have those earrings on me, but you'll see what that is. So digitization is the gateway to AI in medical imaging. And radiology digitized already a long time ago. We're starting, meaning now we know scanners. I don't know. Do you guys have scanners? You do, right? You're an imaging facility. Do you do routine diagnostics on digital? I know, Chris, we had a conversation about implementing some of it. I'm gonna leave this discussion till the end.
Yes, they do.
Perfect. So we are here. We are digitizing the analog, but we're going to be here, and this is direct to digitization imaging for pathology. I'm going to say a few words at the end. So AI in pathology in general, this can lead or help us with improved diagnostic accuracy. We can do image analysis because we have digital slides. And now in the era since ChatGPT became mainstream and natural language processing became mainstream, we can leverage that as well. And these are the three, do I have any bullets? No, but let's unpack. Just the fact that we can read slides on digital, and it is a little bit less pronounced or less visible in a diagnostic workflow where you work one case, then you move on to another case, then you move to another case. And me as a toxicologic pathologist, I work, my workflow is study-based. So I have groups that I compare, and the groups of animals that I look at, they got a specific treatment and I have to compare them. And the mere fact that I can put several of them on the screen and compare directly and not like slides under the microscope while only looking at one at a time gives me an advantage. But obviously, we can do image analysis now. And in the era of generative AI and large language models, we can combine the images and the text and leverage AI even more.
So there's a video about it. At the end, there's going to be a code. You can get those slides and you can watch those videos on your own time. They are all from my YouTube channel. You have to remember to do that. So let's compare to radiology. Do we have any radiologists or radiology imaging specialists on the line today?
Several.
Fantastic. You guys are ahead of the curve. So because you started in the 70s and 80s, and we are only starting now. And by now is actually the first scanner was kind of developed in 1999, 2000, but that was far from mainstream. And now it's 2024 and we are still far from mainstream. So we're 25 years behind. And the funny thing I learned from conversations with radiologists, they had the reverse problem that pathologists have at the moment, because they had to digitize, they had the digital capability to acquire images digitally, but they were not allowed to visualize them digitally. So they were making analog out of digital. We are making digital out of analog. We're using glass slides, and then at the moment we're digitizing them. Image complexity, our pathology images, it depends how you define complexity, because a radiology study can have like different projections. There is cross-sectional imaging, and you scroll stack. It's more like 3D imagination of a structure. Whereas we have single-layer images, but we have a very high resolution. And the complexity is due to cellular detail. Regarding the size, there was a transition from, for resolution and storage of those images. The problem with the radiologists needing to digitize, to make analog the digital, was that the digital monitors didn't have the correct resolution. And now it's not a problem for pathology. It's not a problem either. The resolution we work with is more or less 0.25 microns per pixel to see everything. We do have workflow differences. So we look at single layer images, whereas radiologists can look at single layer, but there's often with CT and ultrasound, it's different variety of images. It's not just flat anatomic pathology image that should be super flat and one layer. In both radiology and pathology, and we are going through this right now, change management is something to keep in mind when we go digital. And I don't know what's going to happen with reimbursement for digital pathology. We can have this discussion at the end, because you guys are now in the process of doing this. But from what I learned from the radiologists I talked to, the digitization actually led to reduced reimbursements, which is less money for us, right? If you want to listen to my conversations with the radiologist, there is a reference podcast video. There's going to be another one published soon. But let's talk about a few real life examples. And we're going to start with image analysis. So I picked examples from a group that is working at Mayo Clinic. They're working with the software called Aphoria, and they did a few cool studies that they published. These are still proof of concepts, but let's start with the eosinophilic esophagitis. So they and this is published in the Journal of Pathology Informatics, and they developed this development and technical validation of an artificial intelligence model for quantitative analysis of histopathologic features of eosinophilic esophagitis. So basically you can do image analysis for everything, and there is a lot of research activity going on. What they went for was something that would very much benefit from image analysis because this, in this case, this esophagitis is a chronic and complex condition. And if it's a complex condition, and the second example is going to be about that as well, the reproducibility between pathologists is difficult, and the more features we need to evaluate, regardless whether it's for diagnostics or for research scoring, the more parameters there are, the the least, like we're less reproducible, and it would benefit from quantification. So this particular project benefited from evaluating complex features consistently. And this software, I don't know, have you heard of Aphoria software? It's a platform for supervised deep learning, meaning you do annotations, you feed the system, you teach the system with examples. You give examples, right? So eosinophilic esophagitis, we have eosinophils, and maybe I should have made it bigger, but basically they're right here. And now on image B, they're painted in blue, and they're not actually painted, they're detected by the software. So what they did there, they implemented cell recognition, and they are showing eosinophil-rich infiltrate. This is B, D, and E. And we have lymphocytes in D are blue dots. So here you should see them. And the eosinophils in B are green dots. So they distinguish eosinophils, lymphocytes, and then later they distinguish different regions of the esophagus. I have to keep deleting my annotations. And they estimated how many of which are in which layer of the esophagus. And basically, then they took all these parameters and had a more reproducible score to deal with the eosinophilic esophagitis. And you should have the reference to this paper in, did I put it? Yes. So everything we're discussing, you will have a reference for. And there is a video for you as well. What about this other project, improved risk? So the previous one, this was just classical image analysis. They knew the features were complex. There was a lot of them. There were different types of cells that needed to be quantified. And they basically automatically detected them, classified, and then had a quantified output and could deal with this in a more consistent way. The second example here, the colorectal cancer, was a good candidate because this is a high prevalence disease, and the histological features are established, so you know exactly what they're evaluating there, and they are also they have predictive value. And the complexity of manual assessment is high. Every time there is a scoring that is difficult to reproduce, it will benefit from image analysis. And here, not only this, they also have predictive value. So the improved risk stratification scheme for mismatch per proficient stage to colorectal cancer using the digital pathology biomarker, and they call it QuantCRC. So what happened here? I was impressed. So I was talking to Rish Pai, who was the co-author and leader of this project at Mayo Clinic. And when I was talking to him, I was impressed that they had actually 15 features. He built a model. It took him half a year, and he included 15 features, 15 different things that he was detecting with the software. They annotated, so they had here carcinoma versus stroma, and they evaluated tumor budding, and they evaluated solid versus glandular growth patterns, signet ring cells, necrosis, mucin production, different stromal subtypes, immune-rich stroma and immature stroma. Then they had TILs, immune cell infiltration, but that's more or less the same, probably. I don't know if maybe this was outside the tumor. Tumor grading, and they included the microsatellite MSI and MSS, stability and instability, and a few other features. Yeah, so to me, the more features, the more complex this model is, and the easier it is for it to fail. But what they did, let me draw it for you. So usually you just give examples of structures in the tissue. So everything that's here other than the instability is image data. And then what they did, they annotated the whole image and gave it a label, stable or unstable. and the label came from genomic data, but they didn't put a specific histopathological feature corresponding to the MSI or MSS. They gave the label to the full image. So I thought it was a pretty innovative way of doing weekly supervised image analysis in a software that was designed for classical supervised with annotations. So they included that as well. So they had these annotations over 24,000, and they had almost 600 cases, 15 features, and they used a database called Colon Cancer Family Registry. This is something that Rishpai was working on. And they trained a prognostic model. So once they had all those features detected consistently, they then combined it to a prognostic model, and they staged it, and they also included the microsatellite instability status. They had a validation, and then they assessed the ability of traditional pathologic features to predict recurrence-free survival. And then they used the quant CRC to do the same. They applied the ASCA risk scheme to predict. And here they did it with image analysis. And it worked. I thought this was a super cool way of incorporating genomic data into image analysis. So that's what they did for colorectal cancer. And this publication was actually from this year. The previous one happened earlier, I think, 2022. Yeah, this was 2022. And you can, of course, listen to the more in-depth conversation. I wanted also to give you an example of a digital-first practice. It's Core Plus in Puerto Rico. And they recently, this year, they published their validation and 3-year of clinical experience in using AI algorithm as second read system for prostate cancer diagnosis, real-world experience. So they have been using a system from the company called IBEX. And you have probably heard about the one that was cleared by the FDA in 2021 from Page AI. And this is the first and only AI tool for pathologists available on the market that has FDA clearance. And it works more or less like this. You have the tumor here, and then the AI shows you with different probabilities what it thinks is more malignant, less malignant. And then I think they already have the Gleason scoring incorporated in that. So in this particular practice, they already started whole slide imaging in 2020. And currently, so this study is from prostate, but they also incorporated the AI for breast, GI, and GI cancer diagnosis. And my speaker was Mariano de Socares. You can have a look at the podcast whenever you have time as well. So they call themselves technology first company. So they would develop their own digital pathology workflow platform, and they also partner with different companies. For example, what they do right now for pap smears, they have 100% screening by AI of pap smears. I don't know exactly how they are incorporating this into their workflow, like in terms of, okay, what then goes to the cytotech, what then goes to the pathologist. But basically all the samples are being screened and by AI, and then there is a decision from AI, okay, does it need to go further in the workflow, or maybe it goes back and just a cytotechnologist evaluates. So pretty cool story. This is an outpatient practice, so it's not a hospital, obviously a little bit more nimble environment, but cool story of somebody who just decided they're going to implement it. And Mariano actually used to work in radiology before he started this practice. He is the CEO. He's not a pathologist, but he has pathologists working there, pretty advanced, different AI partners. So for training those models, and by training models, I mean the new way, the deep learning based way that Margaret was mentioning is now being published. The this like drawing and showing with examples is already a little bit outdated. I'm going to talk to you about so-called foundation models at the end, where the model is supposed to know on its own everything. But the models require quite some images to be trained. And if we only want to have them work well in our lab environment, then they maybe need less examples. If we want them to be more generalizable, like a tool that is supposed to be commercialized, then more examples are needed. And there are two ways of giving the model access to images. There are repositories and there are decentralized ways of training models. So a little table about repositories versus decentralized way before we dive into the table. So repositories is basically you have a huge repository of images. You collect them from all different places, different clinics, to avoid a batch effect. And a lot of people contribute to make this huge repository, and then people can train their models. A repository or like a database is the TCGA, the Cancer Genome Atlas, where we have some slides there. I think it's 40,000 slides for different entities. It's a pretty good sized repository or database of images. But of course, to have a more powerful model, to have something that not only recognizes eosinophils, but also neutrophils and other lymphocytes and other tissue components at the same time, we need more examples and more images. And we can either do this in this way to basically collect a lot of slides and make a repository. So these are our repositories, and this is a decentralized way of training, because for repositories we need a centralized data storage and aggregation, and it requires sharing across institutions. Whereas for decentralized, the data remains local. So this is a little bit less of a hurdle, because if we then later look into GDPR and HIPAA compliance, it's difficult the moment we start sharing, because, okay, who has the permissions? It's complicated, right, from the legal perspective. So decentralized, the data remains local. You don't have to share, but you can still train a model. Regarding scalability and infrastructure, the repositories require significant infrastructure, because the amount of data that then is being stored is huge, is very, very large. One of our images can be, I don't know, 4 megabytes, a lot. For gigabytes, sorry. And then, if we have thousands or now going into millions, this is gonna be a significant infrastructure challenge. Whereas for decentralized way, the computational, so here also both for training and for collecting those images and having them in one place. So training requires computation, and the more you want to teach this model, the more computer power you need. Whereas here, this in the decentralized way, the computational load is distributed across centers and less infrastructure is required. I think I didn't explain exactly what this decentralized, how this is working. It's also called swarm learning. So basically, instead of having a bunch of images and then one model learning from those images, we have those images decentralized in different places. And we have one model that goes, learns, comes back, goes, learns, comes back, goes, learns, and then aggregates the knowledge or weights and biases of those models. So basically, the way this model would then recognize things in the images by going to those images separately. This one is swarm learning. It's different from federated learning. So federated learning is another way of decentralized learning, where you have like a chief model or like chief node that gathers information from the other models or the other partners that are then giving the knowledge or the weights, biases, whatever the deep learning models do, to this one central one. In swarm learning, you don't have the central. You have exchange between everything. So there's no centralization at any stage of this way of developing models. Let's go back to our table and let's review the data compliance and legal considerations. Because when I was talking to Oliver Saldana, he said that was an advantage of the of swarm learning, that this is a lot more difficult because you're not really bringing any image data. You're just bringing the weights and classifications to the model. So there's not really any identifiable information. I don't know if that probably doesn't answer the question, but for repositories, it very much requires adherence to data protection laws because you're giving the images. You're giving, like, you can de-identify them, but basically the image and everything in this image is there. So if there is a problem with the identification, that's our problem. And what he said is that the swarm learning way of doing this complies more easily with data privacy laws, as no patient data is shared. And that it so he is doing this from Europe. So GDPR is the data protection regulation, general data protection regulation in Europe. They're not interested in HIPAA. We are in the US. That's what he told me. So I'm going to give you all those slides, and you can just click on these things, and whatever is interesting to you, you can watch on YouTube or see the summary. But that's what he told me, that this one is easier to comply with regulations, both on a local level and like institution legal level, because nothing is leaving your institution, on local and on more national or continental level in case of Europe. So yeah, that's how we train. Does that mean that we now have to get rid of all those repositories? By the way, have you heard of Digital Diagnostics Foundation? It's a repository, or like a foundation that's building a repository in the US. And this was set up, founded by Dr. Matt Levitt, who is a pathologist and a serial entrepreneur. So Digital Diagnostics Foundation is an organization that is creating a repository. So they are basically getting images from different places, focusing also on the diversity of populations. I think they started in underserved reservation areas. So I don't think anybody had access to pathology images from these regions. And then starting with that, they decided, okay, because those models, when we train them on a certain populations, they may not generalize to other patient populations. So that's like an inherent risk in developing those models, that there can be bias. And to overcome bias, we either make them demographic or population specific, or we include a big diversity of data, whichever study design or approach is appropriate for a particular entity. And these models are not foundation models, but I want to tell you about foundation models. So the models we were talking about were very entity specific, very disease specific. The esophagitis model is only going to work on esophagus, and esophagitis is only going to count eosinophils or whatever they trained for. The colorectal cancer is only going to do colorectal cancer. They're not going to recognize any other cancers. They're not going to recognize organs. And the computer scientists working with pathologists decided, hey, like, then if we keep doing that, then it's going to be an unlimited, immense number of models. And like, who's going to say which one to use? Can't we just have one that does it all? And that is the direction, or these are the attempts that are currently ongoing. And the model that does it all is supposed to be a foundation model. So I did a quick literature search in a software called Undermined. It's an AI-based software that pulls literature in a little bit more structured way than PubMed. It's based on, it has large language model running in the background, and basically goes into the abstracts and pulls stuff that is relevant, and it gives you a relevance score. So all these have pretty high relevance scores and have been published very recently, 2024, 23, 24, 4. Everything except for this one, is this year. And I think it pulled it all from ArcsViv because there you can get access to the full text. But many of these are Nature publications. It doesn't mean that you should not critically verify everything that's published. It doesn't matter where, but Nature carries some weight, right? So foundation models is the new kid on the block in digital pathology and computer vision for pathology, and radiologists on the call. So those foundation models are those models that can do it all. There is a very nice talk by Hamid Tizoush, who used to run the Chemia lab in Canada. Now he is at Mayo Clinic, that I found on YouTube. This is actually from the Pathology Informatics Summit. So his talk that he gave there. And they are large-scale general-purpose deep learning models. Self-supervised learning, so there is no need for annotations. The pathologists don't need to go and draw whichever structures. So they are self-supervised. They have this generalization of capabilities. So it's going to recognize the organ. It's going to recognize the tumor. Maybe it's going to distinguish different things. They're like, it would be fantastic if they would just be like a pathologist, but obviously at the moment they have limited capabilities. But they would recognize tissue, they would highlight tumor, they maybe would divide tumor versus stroma and count some cells, recognize cells. And the thing with them is that they require massive amounts of data. So the current ones that we had in here on our in this, none of these had over 1 million. I think maybe this one was something close to 1 million. No, there was another Virco. I don't see it here. Anyway, the newest one had over 1 million slides, and we said the TCGA database is 40,000 slides, so that's already a lot. But according to Hamid Tizoush, to achieve an industry-level functionality, we would need 5 million whole slide images. Like, who has that? I don't know. Definitely there is no one single repository that has 5 million slides. He estimates the number of the pathology slides that would be needed based on the commercially available foundation models for classification of, or for like dealing, because it's not only classification, with natural images. So he like reverse calculated, okay, if this model that this company, OpenAI or whoever that was, did for natural images, then in pathology images, that would be 5 million. So, and it has to be zero-shot learning. What does that mean? It has to be trained enough so that you don't have to give any examples, right? It knows. It shows you whatever it needs to show you. So zero-shot learning. Currently, regardless that we had like the whole list of publications in the pathology space, there is no model that fulfills all these requirements, but we're going in that direction. And you guys, my radiologists here, you not only have the amount of images that is already going in that direction, you also have different modalities, right? We have flat images, you guys have ultrasound and whatever, right? And you can even do the cardiology stuff in there if you wanted to. Next concept that I wanted to draw for you, because the even newer kid on the block in terms of medical AI, not only image-based, but incorporating everything, incorporating the large language models, natural language processing, and also generative AI, RAG, which is retrieval augmented generation, which is where you ask a large language model to go and search in a specific database to prevent hallucinations and to give specific knowledge to the model. So like everything that we have heard of recently in the commercial AI space, it is being brought to medical space. And obviously I know most of the examples in the pathology side, but and this is called so-called agentic AI. So agentic AI, the easiest way to explain this is AI that orchestrates AI. What do I mean with that? Let me just check. No, here are videos. So I'm going to show you a few videos. But Let's just keep using the image analysis example, and I'll try to draw as best as I can. So let's say, and I'm going to be missing steps. So, but let's say for image analysis, we have to, let's say we already imaged. We have a scans, right? We have to get those scans, get scans. Then we have to pre-process. Then we have to, what do? We do analysis, right? Analysis. And then we generate the results. But for the analysis, we actually would like to include the report as well. And then like do some maybe correlation or not correlation, but verification. So let's say we want analysis, and then we would like to have the, why is it not working? We would like to maybe have RAG, retrieval augmented generation, based on the report, and also maybe based on a literature, right? Because we don't want this to go and hallucinate on its own. We wanted to do literature, and on and on and on and on, right? So normally what would, like, assuming we have all the apps, these are our AI apps, and they're working well, and these are the different AI options that we have. There would be a scientist or somebody responsible for that. They would go here, and then they would do this, and then they would do this. They would do all this, and that would take a lot of time. I cannot delete everything at once, because then my beautiful drawings are going to disappear. But how about we have an AI agent that does that, that does all this stuff and tells one to go to the other, to go to the other, and then come back to the pathologist with something that is pathology readable, path something, report, something that we would have to agree on what is the thing that pathologists could make out of that, some kind of result, right? Let's call it result, just path result. And whatever it's gonna be, it's gonna be path result. So this is our pathologist, but here is a scientist, like a data scientist, computer scientist, that's creating this agent. So our one scientist makes the agent with the current technology, and then the agent takes care of orchestrating all these AI apps, and then gives the result to the pathologist. And this is agentic AI, how I understand it. And I want to show you a few videos. I don't know if you will be able to hear the sound, but there are captions. So the company that is currently entering that market in the pathology space is, I don't know, have you heard of PathChat, an app? This is an AI app, PathChat. Anybody heard that or saw? They didn't announce it. They were kind of in stealth mode. The company is called Modella. .ai, I assume, Modella. And this is the president, Jill Stefanelli, who used to be at Page AI. So what we did with PathChat is an app that reads pathology images. So this is the earring test. We did an earring test. This is my earring. I don't have them to show you, but let's see if we can play it. We're gonna analyze my earrings with PathChat.
There's no guarantee that it'll work.
Oh, so here a picture is being taken, and those who know what that is, they know. And let's see if PathChat will know as my pathologist will know what that is. Used to microscopic images and not images from earrings. It's not the intended use to analyze from earrings. What is the cell in the image? Okay, let's see. PathChat is working. The cell in the image is a multinucleated giant cell with multiple nuclei with a single cell body. PathChat read my earrings correctly. It passes the earring test. PathChat passed the earring test. So it was at the, I was in Utah at the Digital Diagnostics Summit, and Modella had a booth, and they had this setup with this microscope, AmScope. AmScope is a microscope that you can buy on Amazon. It's not like a pathologist level microscope. But what they did with this microscope, they had slides prepared and they had a phone attached to it, iPhone. And this PathChat app was installed on the iPhone. It's basically ChatGPT for pathology images trained with different models. And I'm going to play you this one where Jill says actually which models that is. It's just 1 minute. But basically, I took off my earrings and said, and she was afraid that it's not going to pass. And we did this little video there. But basically, it recognized the multinucleated giant cell that I had on my earring. And you could use a phone through a microscope, like just normal educational microscope, and it would recognize structures. And that's one of their apps. They have other apps, and they have this. They are using this concept of agentic AI to coordinate different apps. And an image analysis example was what Jill gave at this conference when she was speaking as well. So let me just quickly show you what she says about those models for those of you who are interested in what's
I'm here
inside.
with Jill Stefanelli. She's the CEO and president of Modella AI, and here we are at the Modella booth. And we just saw a demo of PathChat. Jill, what's this PathChat based on? What's powering PathChat?
PathChat is based on a couple of underlying foundation models. One is UNI, which is a vision-only encoder. The other is Conch, which is vision matched with medical caption text. So PathChat's basically able to be prompted, describe what you're seeing. It can use UNI to really encode and featureize, and then it uses the Conch to generate the medical text associated with what it's seeing.
So it's basically ChatGPT for pathology. Who's using it?
We have not launched it officially, but we have quite a few beta users where we're just trying to make sure that it's as accurate as it has been in our hands. Things are going really well with that, so we're really optimistic, hopefully before the end of this year, but if not, by the beginning of next year.
I'm looking forward to the launch, and thank you so much.
Yes, thank you, Alex.
So yeah, I see the chat. This is Faisal Mahmoud lab, and the funny story was, so we recorded this video, and I was like, oh, let's post it, and then they both Jill and Richard. Richard is their scientific person, a PhD. I think it was part of his project. This whole came up. I don't know the whole story, but the story about the video was like, oh, let's post it. It's gonna go viral and it's gonna be super fun. And they were like, wait. We need to actually. Oh, and you guys discussed Conch in your meeting earlier. So anyway, they basically sent the video and the picture of my earrings to Faisal Mahmoud and asked, hey, can we put it out? Is it really what the PathChat is saying? And we got the green light, and I was able to post the video on social media. So yeah, I promised that I'm going to tell you a little bit about the direct to digital. I'm very much looking forward to this particular modality. And I learned about it at the beginning of the year. I mean, I've heard about it, but learned about it more in detail from Dr. Richard Levinson. He's at Stanford, and he's been working on glassless pathology and different technologies for quite some time. It was part and still is part of his research. And one of the technologies, MUSE, that's the ultraviolet surface excitation microscopy, he licensed to a company that is bringing a product to the market, and the product is this picture that I showed at the beginning. I'm going to show you in a second. But basically, we are going in the direction of direct to digital, and there are different slide-free options for pathology, slide-free optical microscopy as drivers of diagnostic pathology. This particular one, the MUSE one, I know they are already in clinical trials. The company is called MUSE Microscopy, and you might be seeing some social media content and some interviews with them from my channels if you wish to watch that. Why I love it? Because then we don't have to digitize the analog. This is still the pushback that pathologists, basically, I don't know what your story was when you decided to go digital and try to negotiate that with your decision makers. But in general, whenever you talk about it, it's like, well, you're not taking anything away. The ROI is down the road. Like, we're just adding a scanner on top of what we're already doing, then let's just keep doing what we're already doing. And direct to digital microscopy is going to change that. And that's it from me today. If you would like the slides with the references, videos, and everything that I included for you, you just need to scan this code with your phone. It's going to ask you for your email to access the slides. So if that's okay with you, you're going to be giving me your email, and then you're going to be on my email list. So if you don't want to be on my email list, don't get the slides. If it's okay for you, and what I do with my email list is I send you videos, and you can unsubscribe anytime. So this is for you. I'm going to leave it for a little bit so that you can take a picture of this.